Send a simple text prompt to a large language model and watch as it executes flawlessly in milliseconds. Ask that same model to research a competitor, format the findings, and update a database, and the execution collapses under its own weight, ultimately crashing your application. Wiring a basic API call into a codebase takes minutes. Engineering an autonomous agent that consistently resolves complex tasks is a severe architectural challenge. A common mistake in development is assuming autonomy is achieved by placing a large language model inside an open-ended while loop and giving it unrestricted access to a toolkit. Reliable production autonomy requires strict architectural constraints. This illustrates the naive agent loop. The model receives a prompt, uses a tool, and repeats. As this cycles, the context window fills with unstructured history until memory overflows and the system halts. Even if the context window holds, processing every tool call sequentially forces the user to wait through compounded, stacking latency. Furthermore, when a single tool returns an unexpected error, the unconstrained model attempts to improvise. It frequently hallucinates incorrect parameters and derails the entire execution. To build reliable autonomous systems, developers must abandon the naive loop in favor of 3 specific architectural patterns. The solution requires shifting the cognitive load away from a single massive prompt and distributing it across discrete, manageable operations. This grid introduces the new architecture from the ground up, starting with a single, stateless unit of work, Node A. This forms the basis of our first architectural pattern, operation chaining. Instead of one massive task, the workload is broken down. Node A executes a highly specific data extraction, formats the result, and passes it forward to Node B. The output payload of the first state serves as the exact structured input for the next state. This prevents context bloat entirely. Because Node B only receives the clean JSON output from Node A, the context window refreshes completely at each step. Chaining heavily isolates instruction sets. The model applies its full reasoning capacity to one distinct task at a time. Unlike the naive loop, the chained model never struggles to extract data, format tables, and synthesize conclusions simultaneously. The correct mental model for designing this sequence is a traditional state machine. This modularity allows engineers to test individual steps in isolation without executing the entire end-to-end workflow. By enforcing predictable transitions between tasks, chaining converts a chaotic, open-ended loop into a linear, reliable software pipeline. A strictly linear chain solves stability, but it cannot handle diverse, unpredictable user requests on its own. To handle variance, the architecture incorporates the second pattern, conditional routing. Here, a new router node sits at the very beginning of the sequence. The router uses the LLM strictly as a classification engine. It performs no active task execution. It evaluates the incoming user request, identifies the intent, and determines the single best execution path. Once classified, the router directs the payload down a specific predefined pathway. This eliminates the need for a massive universal system prompt. The workload is instead handled by specialized, narrow subagents. These subagents only load the system instructions and tools strictly required for their assigned route. The LLM makes a probabilistic routing decision up front, which then triggers a highly deterministic software execution. This routing logic bounds the potential error space by keeping irrelevant tools explicitly hidden from the model. By dividing and conquering, conditional routing scales the system's capability, ensuring it only deploys the exact intelligence required for the specific task at hand. Processing data sequentially creates a physical bottleneck. Stacking LLM calls directly stacks user-facing latency. To eliminate this bottleneck, we implement the third architectural pattern, parallel execution. This diagram shows a scenario where a routed task requires querying multiple independent data sources. The path splits into 3 concurrent branches. This is a fan-out mechanism. The system launches multiple asynchronous API requests to external tools at the exact same time. Each branch operates completely independently, sharing no context or memory during execution. In the fan-in phase, the system waits for all asynchronous promises to resolve, then converges the resulting data payloads into a single synthesis node. Looking at this timeline chart overlay, the total execution time drops significantly compared to processing each step sequentially. This concurrency is only reliable because the prior routing step cleanly identified which operations were truly independent. While parallel execution consumes more compute tokens simultaneously, the reduction in wait time dramatically improves the end-user experience. Parallel execution prevents complex data-gathering agents from becoming unusably slow, proving that true scalability requires architectural concurrency. This is the complete directed acyclic graph, or DAG, combining the router, the parallel branches, and the sequential chains into one cohesive system. High-performing autonomous agents function as an orchestration of specialized, highly constrained workflows. Because this graph is directed and acyclic, data only flows forward toward a resolution, entirely preventing infinite loops. This structure provides a distinct operational advantage for engineering teams by making the system observable. When nodes are isolated and state is passed explicitly, tracing an error back to its source becomes a straightforward diagnostic process. This deterministic structure forces an AI agent to behave, fail, and be maintained exactly like traditional software systems. In this simulated debugging trace, a single node fails within a parallel branch. The failure remains isolated, preventing a total system crash. Engineers can inspect the exact JSON input and output payload at this specific point of failure. They can adjust the prompt or the tool logic for this single node without breaking or altering the surrounding workflows. Adopting chaining, routing, and parallelization permanently transitions the focus from fragile prompt tuning to robust system design. Reliable AI autonomy isn't magic. It is fundamentally a product of providing the language model with better, highly disciplined architectural structure.